November 1929, Philadelphia, Pennsylvania. Mining engineer Daniel Barringer died a broken man. For 26 years, he had poured his fortune into a massive crater in Arizona, chasing a theory the world's top scientists called a fantasy, and his final drill had come up empty. The British geological community, who had mocked his obsessive hunt for a space rock, felt vindicated. Their verdict was final, that the crater was just a strange volcano. They had no idea his failure was the final tragic chapter in the story of how the British mocked U.S. research on a volcano. Days later, Americans proved it came from space, forever changing our view of the cosmos. Gilbert's proclamation. The intellectual climate of the late 19th century was one of strict terrestrial focus. The skepticism in the global geology community toward any cosmic explanation was not just palpable, it was a foundational principle. The prevailing European and British scientific view held that the heavens were a place of divine, clockwork order. The real action, the violent shaping of worlds, happened underfoot through volcanoes, earthquakes, and erosion. Catastrophic events from space were seen as the stuff of ancient myths and religious texts, relics of a superstitious past, not concepts for serious scientific inquiry. To suggest that a rock falling from the sky could carve out such a feature was to invite ridicule. It was seen as a return to a pre-scientific, catastrophist worldview that men of reason had spent a century dismantling. Gilbert, embodying this terrestrial bias, began his investigation with a preconceived conclusion. He was a brilliant and meticulous observer, but he was looking for evidence to confirm what he already believed. He observed the raised rim of the crater, a feature common to many volcanoes. He noted the vast blanket of ejected rock and soil thrown for miles in every direction. He even studied the moon through telescopes, concluding that its craters, too, were likely the result of ancient volcanic activity. But what truly sealed his judgment on the Arizona crater was what he didn't find. He reasoned that if a colossal iron meteorite had created this hole, it must still be buried beneath the floor. Using rudimentary magnetometers and gravitational surveys, he painstakingly searched for a massive iron anomaly, the theoretical cosmic bullet that would have delivered the blow. His instruments detected nothing of significance. Furthermore, he saw no evidence of the unimaginable kinetic energy an impact would require, because at the time, no one truly understood what that evidence would even look like. His final report was a landmark of geological reasoning. He declared the feature a cryptovolcanic structure, the result of a massive, superheated steam explosion from deep within the Earth that had catastrophically blown a hole in the desert floor. In the final analysis, the Great Crater was a uniquely American, but entirely terrestrial phenomenon. For the scientific establishment, both in the U.S. and across the Atlantic, the case was closed. The official narrative was written, and for over a decade, it was accepted as gospel. But 1,300 miles away, a Philadelphia mining engineer named Daniel Barringer heard stories of the crater and, more importantly, of the strange metallic fragments that local ranchers found, scattered like celestial shrapnel around its rim. Barringer was not a government geologist bound by academic dogma. He was a pragmatist, an entrepreneur, a man of industry who had made his considerable fortune by understanding how to pull valuable metals from the ground. He was a graduate of both Harvard and Princeton, a man of intellect and society, but his mind was wired for business and opportunity. When he had a sample of the strange iron analyzed, the results were an electrifying jolt. The fragments were 92% iron, 6% nickel, with trace amounts of platinum and iridium, a chemical signature that did not exist in terrestrial iron. It was the unmistakable composition of a meteorite. Staring at that lab report, Barringer didn't see a scientific curiosity. He saw a 10 million ton cosmic cash register buried just beneath the Arizona sand. In 1903, Barringer and his partner, the physicist Benjamin Tilghman, did not write a paper. They filed mining claims. They secured the rights to 640 acres of land, encompassing the crater and its immediate surroundings. He formed the Standard Iron Company, secured investors with promises of an extraterrestrial bounty, and set out to do what the esteemed G.K. Gilbert had failed to do: prove the crater was an impact site, and, more importantly, get fabulously rich by mining the asteroid that made it. What neither man knew in that moment was that this business venture would morph into a multi-decade obsession, a personal crusade that would pit one man's iron will against the unyielding rock of scientific consensus. Barringer wasn't just drilling for a meteorite. He was drilling into the very heart of a deeply entrenched international scientific belief system. The British geological societies and prominent European academics watched with detached, slightly smug amusement. They viewed Barringer's project as a classic example of foolish American ambition, a wild goose chase for a space rock that science had already proven wasn't there. They were confident in Gilbert's work, in the steady, earthbound forces they understood. The impossible, they believed, was just that, impossible. The story of Barringer's quest is not merely a technical tale, it is a narrative of institutional resistance, personal sacrifice, and the dogged pursuit of a revolutionary idea. He arrived in the desolate Arizona landscape with drilling rigs and a crew of roughnecks, ready to unearth a cosmic treasure. The desert heat was oppressive, the conditions were crude, but Barringer's optimism was boundless. He had studied the crater's geology, noting its asymmetry, and calculated that the impactor had likely come in at an angle from the north. He therefore pointed to a spot beneath the crater's southern rim. There, he told his investors, the main body of the meteorite, a colossal mass of iron and nickel worth hundreds of millions of dollars, was waiting for him. All he had to do was dig. The steam engines roared to life, the drills fired up, biting into the desert floor, beginning a journey into the earth that would ultimately consume Barringer's life, his fortune, and his reputation. The entire scientific world was watching, confidently waiting for him to fail. The initial drills were tantalizingly encouraging. They pulled up cores of crushed and pulverized sandstone, exactly what one would expect from a hypervelocity impact. Then, at depths between 300 and 500 feet, the drill bits started hitting fragments of meteoritic iron mixed with shattered rock, some weighing several pounds. For Barringer, this was the irrefutable confirmation he needed. He wrote jubilant, triumphant letters to his investors, proclaiming that the prize was just a little deeper. More troubling, however, was the sheer volume of underground water they encountered. The drill holes repeatedly flooded, turning the rock flour into a thick slurry that seized the drill bits and slowed progress to a crawl. The financial burn rate was enormous. Every foot of drilled rock cost a fortune in labor, equipment, and the constant, frustrating battle against the desert's hidden water table. Months of struggle turned into years of relentless effort. The first drill hole was abandoned, then a second, a third. The skepticism from the academic world, particularly from British journals that occasionally reported on his folly, grew louder and more condescending. They pointed to his struggles not as unforeseen challenges, but as the predictable consequence of chasing a ghost. But Daniel Barringer was not a man easily deterred. He was possessed by a single, magnificent idea. He could feel the cosmic iron in his bones, just beyond the reach of his struggling machinery. He stubbornly refused to believe that the thousands of tons of iron shale scattered across the landscape were the only remnants of the impact. Logic, as he saw it, dictated that the main mass, the engine of the event, had to be down there. What he didn't understand, and what no scientist at the time could possibly comprehend, was the terrifying physics of such an immense impact. The energy released was not like a bullet hitting sand. It was an explosion more powerful than any weapon on Earth, a force so great it could vaporize solid iron in the blink of an eye. The treasure he was hunting for, with every fiber of his being, no longer existed. He was digging his own financial grave, one drill hole at a time. The deeper he went, the more the evidence mounted against his specific goal, yet the more his faith in the general theory grew. This stubborn faith would become his defining characteristic, and his ultimate undoing. The real answer was not deeper in the earth, but the proof would have to wait for a new kind of man-made explosion to reveal itself, digging for a dream. The story of Daniel Barringer's excavation is one of the most persistent and ultimately heartbreaking endeavors in American scientific history. From 1903 until 1929, for 26 grueling years, the vast, silent crater was not a serene monument, but an active, noisy, and dirty industrial site. The encampment was crude, a small outpost of humanity against the vastness of the Arizona desert. Men lived in rough-hewn bunkhouses, working under a sun that baked the landscape to a brittle brown. The facility itself was little more than packed dirt floors beneath a palm-thatched roof, the air thick with the smell of steam, oil, and sweat. The constant chugging of engines powering the drills was the relentless soundtrack to their lives. Yet for Barringer, this noisy, dusty patch of desert was a field of dreams. He poured every dollar he had, and many he didn't, into the project. His initial investment of a few $100,000 quickly spiraled into a debt that would be equivalent to many millions in today's currency. All told, he would spend over $600,000, a staggering fortune at the time, enough to build a skyscraper. What kept him going? What fueled this incredible, decades-long gamble that flew in the face of all accepted science? It was the tantalizing stream of evidence his drills kept uncovering, clues that seemed to promise a colossal reward just beyond his grasp. At a depth of 410 feet, the drill bit hit something so hard it could barely make a scratch. They had found a large meteorite, a tangible piece of the cosmic puzzle. But it was only one piece. Time and again, the drills would churn through hundreds of feet of shattered rock. Rock that had been subjected to forces so extreme it had been reduced to a fine white powder, something geologists called rock flour. Then, they would hit patches of meteoritic material, which Barringer called subsurface detritus, confirming they were on the right track. Each small discovery was a victory that Barringer, a master salesman as much as an engineer, would leverage to calm nervous investors and secure more funding. He was in a constant battle on two fronts, against the unforgiving geology below his feet and against the mounting skepticism from the entire scientific community looking over his shoulder. The most prominent scientific journal of the era, Nature, based in London, followed the Arizona crater story with a certain detached superiority, a tone of intellectual condescension. Articles would occasionally appear, framing Barringer's work as a peculiar American spectacle, a prime example of New World ambition, untempered by Old World scientific rigor. The consensus among British and European geologists remained firmly, unshakably, with Gilbert's volcanic theory. They argued that the meteoritic iron fragments Barringer found were incidental, cosmic debris that just happened to fall in or around a pre-existing volcanic structure, a phenomenon they called a geological coincidence. To them, Barringer wasn't a pioneering researcher charting new territory. He was a common treasure hunter blinded by the glitter of celestial iron, stubbornly misinterpreting every piece of data to fit his wild, unsubstantiated, and frankly, ridiculous theory. The skepticism in the room of global geology was palpable, and Barringer was the lone man shouting against the crowd. More troubling was the fact that Barringer's own evidence was beginning to contradict his central hypothesis. His entire business model was based on finding a single, massive, mineable body of iron. Yet, his drills were only finding scattered fragments intimately mixed with pulverized rock. His own lead driller, Samuel J. Holsinger, a practical man who had spent years fighting the stubborn rock, began to have serious doubts. In detailed letters to Barringer, Holsinger theorized that the impactor might have been a loose cluster of smaller meteorites, or that it had catastrophically shattered upon impact, creating a pancake of debris rather than a solid mass. Barringer angrily dismissed these ideas. His financial model, his solemn promise to investors, and his entire life's work were staked on the existence of a single recoverable asteroid worth a fortune. To accept that the main mass had been destroyed was to accept total, humiliating failure. The human element of Barringer's quest deserves emphasis. This was not a remote investment for him. He was not an absentee owner dictating orders from a comfortable Philadelphia office. He spent vast amounts of time on site, living in the same basic conditions as his men, personally overseeing the drilling operations with an obsessive eye for detail. He meticulously logged every sample, every change in rock strata, every mechanical failure. His correspondence from this period reveals a man of incredible intelligence and unyielding resilience, but also one who was slowly being crushed by the immense weight of his own convictions. He wrote scientific papers, presenting his findings at conferences, fighting a lonely intellectual war against the Goliaths of geology. He pointed to the inverted stratigraphy of the crater rim, where layers of rock were flipped upside down, with older rock on top of younger rock, as undeniable proof of a massive explosive upheaval that no steam vent could create. But the establishment geologists simply shrugged, attributing it to the complex, unknowable mechanics of a crypto-volcanic eruption. The final desperate chapter of his quest began in 1928. After years of struggling with vertical drill holes that either flooded or became hopelessly stuck, Barringer commissioned a brilliant but eccentric astrophysicist named Forrest Ray Moulton to calculate precisely where the main body of the meteorite ought to be. Moulton was one of the few respected academics who took Barringer's impact theory seriously. He spent months performing complex calculations, factoring in atmospheric drag, the angle of entry, and the incredible, almost unimaginable physics of the impact itself. He understood that the energy of the impactor was a function of its mass and the square of its velocity. The speed, he realized, was the truly destructive variable. His final conclusion was a devastating mathematical death blow to Barringer's dream. Moulton calculated that the impactor, which he estimated to be around 300,000 tons traveling at nearly 10 miles per second, would have released an energy equivalent to a 10 megaton bomb. The kinetic energy would have been so immense that upon impact, it would have been almost entirely and instantaneously converted into heat, vaporizing the vast majority of the meteorite in a fraction of a second. A fountain of white spray, of molten iron and incandescent rock vapor would have erupted from the impact point. The treasure Barringer had been searching for 26 years did not exist. It had vanished in a flash of cosmic fire. Moulton's report stated plainly that any surviving fragments would be scattered and mixed with the country rock, but the mother lode was gone. Barringer's reaction was one of complete and utter rejection. His mind, so logical in many ways, simply could not accept this conclusion. He accused Moulton of being a purely theoretical man, an ivory tower academic who didn't understand the practical realities of geology and mining. He believed the hard numbers and the cold physics were wrong, and that his gut, his intuition as a miner, was right. He staked everything, his last dollars, his last hopes, his very reputation, on one last deep shaft aimed at the center of the southern rim. In 1929, the final drill bit hit a depth of 1,376 feet and found nothing but undisturbed primordial sandstone. They had drilled past the zone of impact. The money was gone. The investors were gone. The last hope was gone. The news was catastrophic for Daniel Barringer. For 26 years, he had held on to his belief with a grip of iron. On November 30th, 1929, just weeks after receiving Moulton's final, damning report and hearing of the drill's ultimate failure, he suffered a massive heart attack and passed away. His family always maintained that he was taken by a broken heart, a man who had given his life for a theory that the world dismissed as a fantasy and that now seemed, even by his own exhaustive exploration, to be a failure. The mockery of the scientific establishment seemed entirely justified. The great American dreamer and his million-dollar hole had come up empty. But what no one, not even the brilliant Moulton, knew in that moment was that the proof of impact wasn't buried deep underground. It was sitting on the surface, scattered all around, waiting for a new kind of science to unlock its secrets: atomic Rosetta Stone. For 3 decades after Daniel Barringer's passing, the crater bearing his name sat in a state of scientific limbo and quiet defiance. His family, though heartbroken and financially drained, never lost faith in his theory. They took over the property, fenced it off to preserve it from scavengers, and turned it into a privately owned tourist attraction. In a bold act of posthumous loyalty, they officially named it Meteor Crater. This name was not just a marketing tool. It was a statement of defiance, a direct challenge to the geological establishment which still clung stubbornly to the volcanic origin theory. To the scientific world at large, the crater was a settled issue, a closed chapter. It was a fascinating anomaly, yes, but its earthly origins were considered fact. The story of the obsessive mining engineer who chased a phantom meteorite served as a cautionary tale in university geology departments, a lesson against the dangers of letting a wild theory run away with reason and good sense. During these intervening decades, other researchers came and went. A dedicated meteorite hunter named Harvey H. Nieninger spent years combing the plains around the crater, meticulously collecting over 20 tons of meteoritic material. He mapped the distribution of the fragments and became another vocal champion of the impact theory, but he lacked the definitive geological proof to overturn Gilbert's powerful legacy. The impossible was about to become routine, but the catalyst would come from the most unlikely and terrifying of sources: the fearsome new power of the atomic bomb. The legacy of the Manhattan Project extended far beyond geopolitics and warfare. In the scorched deserts of New Mexico, at the Trinity site, and later at the Nevada test site, humanity began creating its own impact craters. These weren't formed over millennia by steam or lava, but were blasted into existence in microseconds by explosions of unimaginable power. For the very first time, scientists could study the immediate effects of a hypervelocity, high-pressure, high-temperature event on common rock. Geologists swarmed these man-made craters, studying the strange and violently altered minerals they found, inadvertently creating a brand new field of science: shock metamorphism. They were writing a new language of destruction, learning to read the grammar of catastrophe as it was written in stone. What they didn't realize at first was that they were stumbling upon the Rosetta Stone needed to finally translate the 50,000-year-old story of the Great Arizona Crater. The narrative now shifts to a young, brilliant geologist in the 1950s named Eugene M. Shoemaker. As a student, Shoemaker had made a pilgrimage to the crater and, like Barringer before him, was utterly captivated by its sheer power and scale. He intuitively felt that the volcanic theory was wrong, that the sheer degree of pulverization and the vastness of the destruction pointed to something far more violent and instantaneous. But intuition wasn't proof. While working on his PhD at Princeton, Shoemaker began studying the craters formed by underground nuclear tests in Nevada. He spent weeks crawling around these atomic scars, mapping their structures, and analyzing the bizarrely transformed rocks. He saw sandstone that had been fused into a glassy substance later named impactite. He saw rocks that had been fractured in unique conical patterns, radiating from the point of impact like fossilized sound waves, which he would later formally name shatter cones. But the most important discovery, the one that would change everything, was what had happened to a common, everyday mineral: quartz. Under normal geological conditions of heat and pressure, quartz is one of the most stable minerals on Earth. But Shoemaker found that under the instantaneous, extreme pressure of a nuclear blast, pressures exceeding 500,000 pounds per square inch, pressures greater than those found at the bottom of the deepest ocean trench, the atomic structure of the quartz crystal was violently squeezed and permanently rearranged into a new, much denser form. This new mineral was called coesite. The technique to identify it under a microscope was complex, but its implication was breathtakingly simple and revolutionary. Coesite could only be formed under conditions of immense, instantaneous pressure, the kind of pressure that simply does not exist in any known volcanic process on Earth. Imagine crushing a lump of coal into a diamond with a single hammer blow. This was the geological equivalent. The specific settings of a nuclear blast, unfathomable pressure and heat delivered in a fraction of a second, were the only known terrestrial process that could create it. It was a unique signature, a geological fingerprint left behind by an almost unimaginable event. In that moment of understanding, Shoemaker had the key. He had seen the effect. Now he needed to find the same effect at the one place that had haunted his academic imagination. The story of how he connected the atomic age to the cosmic mystery is not just a scientific tale. It's a detective story of the highest order. In 1960, Eugene Shoemaker turned his full attention back to the Arizona crater. Armed with this powerful new knowledge, He proposed a radical PhD thesis. He would conduct a direct comparison of the geology of the Nevada nuclear test sites with Barringer Crater. The skepticism in the academic world was still present, but the world had changed. The space race was on, rockets were piercing the heavens, and the idea of cosmic collisions no longer seemed as fanciful as it once had. The universe suddenly felt like a much more dynamic and dangerous place. Shoemaker secured permission from the Barringer family, who were thrilled that a serious scientist was taking their father's theory seriously again. He set out to collect samples from the crater floor and rim. He wasn't drilling deep into the earth like Barringer. He was looking at the surface, at the very rocks that Gilbert and a generation of geologists had dismissed as unremarkable. He gathered samples of the Coconino sandstone from within the crater, the same white, pulverized rock that had been dismissed for over half a century. Back in the lab, he meticulously sliced the rocks into paper-thin sections, so thin that light could pass through them. He placed them under a powerful petrographic microscope and began the painstaking hunt. He was looking for microscopic crystals with a unique refractive index, the telltale sign of the shocked quartz he had become so familiar with in Nevada. Slide after slide revealed nothing but normal, fractured quartz. The search was tedious and frustrating. And then he found it. There, in a piece of sandstone from the Arizona desert, was a tiny, undeniable crystal of coesite. It was the smoking gun, the final, irrefutable proof. The existence of coesite at Barringer Crater meant that the rock had been subjected to the same kind of instantaneous, ultra-high pressures found at the heart of a nuclear explosion. No volcano, no steam eruption, no slow geological process native to our planet could do that. Only one thing could: the hypervelocity impact of a massive object from space. In that single microscopic crystal, Daniel Barringer's lifelong obsession was vindicated. His theory, mocked for half a century, was proven to be spectacularly correct. The British and European geologists, who had dismissed his work as foolishness, were shown to be bound by an outdated Earth-centric dogma. The Americans, the wild-eyed dreamers, had been right all along. Shoemaker's discovery didn't just solve the mystery of one crater. It blew the doors wide open on a whole new understanding of Earth's violent and cosmic history. The proof had been there all along, not in a buried treasure of iron, but in the very fabric of the stones scattered across the crater floor. All it took was a new way of seeing, a new language learned from the atom. The discovery would do more than just rewrite textbooks. It would help take humanity to the moon. A legacy written in the stars. Eugene Shoemaker's discovery of coesite, later followed by the discovery of an even higher pressure mineral called stishovite at the crater, was more than just the solution to a 70-year-old mystery. It was a seismic shift in all of planetary science. The paper he published in 1960 sent shockwaves through the geological community. The evidence was ironclad, written in the atomic structure of the rocks themselves. The debate was over. Barringer Crater, the site of so much ridicule, obsession, and financial ruin, was officially and forever recognized as the first proven meteorite impact crater on Earth. The legacy of Daniel Barringer was transformed overnight. He was no longer a failed businessman who perished chasing a foolish dream. He was heralded as a scientific visionary, a man decades ahead of his time, who had correctly identified a fundamental truth about our planet that the entire scientific establishment had arrogantly missed. In the final analysis, his commitment to his theory, while financially ruinous, had paved the way for one of the greatest geological discoveries of the 20th century. What happened next cemented the crater's place in the annals of human history. As the United States raced to fulfill President John F. Kennedy's audacious promise of landing a man on the moon, NASA's engineers and scientists faced a critical, unknown variable. What was the lunar surface actually like? Telescopes showed that it was covered in craters of all sizes. But were they volcanic, as so many on Earth were still thought to be? Or were they the result of impacts? This was not an academic question. The lives of the astronauts depended on the answer. Shoemaker, now a celebrated figure and a founder of the U.S. Geological Survey's astrogeology branch, argued passionately that the moon was a battered, ancient world, its face scarred by billions of years of cosmic bombardment. He proposed that Barringer Crater was the perfect analog, the best and most accessible place on Earth to understand the lunar landscape. NASA agreed. The story of how the crater became a vital training ground for the Apollo missions is a remarkable chapter in the history of space exploration. Starting in the mid-1960s, every astronaut destined for the moon, from Neil Armstrong and Buzz Aldrin of Apollo 11 to Gene Cernan of Apollo 17, was brought to the crater's floor. There, with Shoemaker and other geologists as their guides, they learned the brand new science of impact geology. They practiced navigating in the rugged, alien-like terrain, their bulky training suits a stark white against the red Arizona rock. They learned how to identify the features of an impact site, the overturned flaps of rock, the presence of fallback breccia, the subtle signs of shocked minerals. They were trained to select the most scientifically valuable rock samples, distinguishing between native rock and the strange altered stones created by an impact. They were, quite literally, walking in the footsteps of a cosmic event to prepare them for walking on another world. The irony was profound. The very site that was once dismissed by mainstream science as a terrestrial anomaly was now the essential classroom for humanity's first steps off its home planet. This new understanding, born in Arizona and confirmed on the moon, fundamentally changed our view of the solar system. Scientists, now armed with the knowledge of what to look for, coesite, stishovite, shatter cones, inverted stratigraphy, began re-examining other strange circular structures around the globe that had long puzzled geologists. The results were staggering. The Sudbury Basin in Ontario, Canada, a massive 200-kilometer-wide structure and a major source of nickel ore, was proven to be a colossal, ancient impact crater. The Vredefort Dome in South Africa, another giant circular feature, was also reclassified as the remnant of an even larger impact. The list grew and grew. Today, thanks to the paradigm shift that started at Barringer Crater, we have identified over 190 confirmed impact craters on the Earth's surface. We now understand that major impacts are not rare, freak events, but a fundamental geological process that has profoundly shaped our planet's history and the course of evolution itself. This revolution in thinking led directly to the Alvarez hypothesis in 1980, the theory that a massive asteroid impact in the Yucatan Peninsula 66 million years ago caused the mass extinction event that eliminated the dinosaurs. That theory, once as controversial as Barringer's, is now the consensus view, thanks in large part to the foundational science of impact dynamics that Shoemaker pioneered. We now understand that Earth is not an isolated island, but an active participant in a cosmic shooting gallery. The evidence was always there, etched into the planet's crust, but our thinking was too terrestrial, too limited, too uniform. Barringer and Shoemaker forced us to look up and recognize the potent, creative, and destructive power of the cosmos. And what of the object that started it all? Modern science has painted a remarkably clear and violent picture of the event. About 50,000 years ago, a nickel-iron meteorite, roughly 150 feet in diameter and weighing 300,000 tons, slammed into the atmosphere at a blistering 27,000 miles per hour. It struck the grassy plains of northern Arizona with the force of about 10 megatons of TNT, a blast hundreds of times more powerful than the atomic bomb that fell on Hiroshima. The impact excavated 175 million tons of rock in seconds, creating a fireball that would have incinerated all life for miles around, and a shockwave that flattened a forest of prehistoric trees. The result was the nearly mile-wide crater that we see today. As Moulton had predicted, and Shoemaker had proven, the vast majority of the impactor was vaporized, leaving only the scattered fragments that had led Daniel Barringer on his obsessive and ultimately tragic quest. So, are we missing a key detail here? People watching this might be wondering how an entire generation of the world's best scientists could have missed something so obvious. The thing is This wasn't an overnight discovery that everyone suddenly accepted. It was a slow, brutal, 60-year fight against established dogma. Barringer's story is a powerful lesson in the nature of scientific progress. It is often driven by outsiders, by determined individuals who are not afraid to challenge the consensus and pursue an idea that seems ridiculous to their peers. But it also shows that intuition and passion are not enough. You need hard, irrefutable evidence. Barringer had the right idea, but the wrong method, blinded by the promise of a treasure that didn't exist. Shoemaker had the right method and the benefit of new, atomic-age knowledge. Together, their stories form the complete narrative, a tale of vision, obsession, failure, and ultimate spectacular vindication that not only solved the riddle of a hole in the desert, but forever changed how we see our world and our precarious place in the universe. Did Barringer's obsessive quest help or hinder the ultimate discovery? Hit like and subscribe, and let us know in the comments if you believe we're blind to another great scientific truth today.